All right, Unit 3, Lesson 5, the last lesson of this unit. It's about polynomial application problems, which probably mostly revolve around optimization. So we're going to be trying to optimize volume in this case. These first couple of examples are about a box that we're going to create from a piece of paper, a piece of cardboard, or something like that. So then we want to optimize the volume. So what should the dimensions be of that box? So you need your TI Inspire. If you don't have it, you should pause and grab it to make sure you have it handy. So let's look at example 1. It says an open box can be made by cutting squares out of the corners of a 9 by 12 rectangular sheet of cardboard and folding up the sides. So this over here on the right hand side is supposed to be representing our 9 by 12 sheet of cardboard, and we are cutting out these squares right here. Right, and so we're calling this, each square removed from the rectangle has a width of x, so this is x and this is x. We want to write an equation that represents the volume. So volume is length times width times height, just as a reminder to all of you. And if we're removing this, we're going to fold, let's see here, we're going to fold this section up, right, and this section up here. And those two sides are going to become these shorter edges here. Then this part is going to be folded up, and this part's going to be folded up, and those would be this section here and here, right? And so this section in the middle is the base or the bottom of the box that we're going to create, so that's the bottom there. So if we look at it, these two x's, they fold up and they come together to make these corners, right? These two x's fold up, come together. So my height is actually x, so it's length times width times height, so my height is equal to x. Now what is my length and width? Well, this was originally 12 inches right here, but I'm going to subtract an x and subtract an x, so that's going to be 12 minus 2x. I'm going to run out of space here, and then this width or length, whatever you want to call it, again we're subtracting an x and subtracting an x, so this little width right here is going to be 9 minus 2x, and then the height that's going up right there is going to be x. So length times width times height, 12 minus 2x times 9 minus 2x times x is how we would find the volume. And what do we do then? Well, in order to figure out what the largest possible volume could be, we need to graph this. And when you're graphing, I want you to think about what the x-axis represents and what the y-axis represents. Here, this is the y-axis. So what does the y-axis represent? It represents the volume in inches cubed, right? So it says 9 inches by 12 inches, so it's representing inches cubed. What is the x-axis representing? Well, the x-axis is representing whatever x is, and in this case, x is the height, right? So x is representing the height in inches. Now, we have a 0 right here at 6, we have a 0 here at 4.5, and we have a 0 here at 0. So if you kind of know that before you even go to your window, right, we have a 0 at 0, 4.5, and 6. So here's our, we set that equal to 0, we get a 0, 6, a 0, 4.5, and a 0, 0. The next thing you could do is figure out, you know, if we were to multiply that out, we would have negative 2x times negative 2x times x. So negative 2x times negative 2x times x would be positive 4x cubed. So the leading coefficient is positive and it's a cubic, which means your end behaviors need to be going in opposite directions. Because it's a positive leading coefficient and it's a cubic, we need to start by going upward and we need to end by going upward. So we're going to go up and then we're going to go down and then we're going to go back up again. Right? So this is what that graph is going to look like. So now, if I want to find the largest possible volume, I'm looking for this point right here. Right? This y-axis is representing volume. This would be the largest possible volume. So it's between 0 and 4.5. All of these are negative volumes, those don't make sense. And this goes on infinitely, but these values over here don't make sense because when you put in an x that's bigger than 6, you're going to get two negative answers, which is why we have a positive volume, but it doesn't make sense. You can't have two negative dimensions in there. So the only portion of this graph that is going to be useful to us, so the practical domain and practical range have to come from this section right here. So my domain is only going from 0 to 4.5. I'm excluding both of those because I don't want a volume of 0. And my range is going to go from a volume of 0 to whatever I get. Now I have to plug it into my calculator to figure it out. So what is this point right here? So I can't show you a calculator, so you're gonna have to pause, grab your calculator, input this equation, make sure you're putting multiplication signs between those parentheses, input that equation, and then graph it and see what you get. So pause and try that now. Okay, apologies for everything being crammed onto this one little piece of paper, but I went ahead and plugged it into my calculator. This is what I got. I got that point to be 1.697 and 81.872. This 81.872 is the maximum volume, so I filled that in for my practical range. It can go from 0 to 81.872. This is inclusive because it can actually equal that volume. We don't want a volume of 0, so I kept that as exclusive. This value right here, that is the width of the square to be removed in order for the box to have a maximum value. Or in other words, that's also the height, right? So we could have said it's the height or it's the width of the square that we are removing. It's going to be 1.697 inches by 1.697 inches. And then what are the dimensions? Well, you have to take this number and you have to plug it into x and plug it into x to get your 3 dimensions. So I already calculated that, and you should go ahead and try it because you're going to have to do that on your own on an assessment. So you should pause, practice that, and see if you're getting the same answers. Okay, so that first example was an open box, open top for a box. It didn't have a top on it. This second example is when we take a rectangular piece of paper and we cut it so that we have a box that has a lid or a top, right? So we want a top on top of our box, so it's closed. So all 6 sides are there: top, bottom, right, left, up, down. So we have 2 congruent squares that are removed from one end of a rectangular piece of cardboard that measured 10 inches by 20 inches. So you can see this is the shorter side, this is 10 inches, this right here is 20 inches. We are going to remove this piece here and this piece here, so we're going to call that x and this x. So this section now right here is just going to be 10 minus 2x, right? So I'm going to erase oops, sorry, I'm going to erase this 10. I guess I can't erase it. I'm just going to make this 10 minus 2x here. Now this portion, I'm going to subtract my x here. Now what happens? Well, if this whole thing is 20, I need to fold it in half. So this is 10 and this is 10. And then this 10 is the entire length, but then I subtract an x from it. So to get this portion right here, I take the entire 10 and I subtract the x. So this purple portion is just 10 minus x. Okay, so I had to fold the paper in half. So I get 10 and 10, and then these 2 corners are being folded up. So this right here is being folded up. This is its opposite on the other 10, right? So we're taking an x from each side, and these 2 sides are being folded up. This is being folded up. They're being cut out of this. So these are being cut out. So this top right here, this is the top, and it's coming over top of the bottom. In class, you're going to fold this. We're actually going to cut it out. You could try it yourself, like cut out these rectangles, see what happens to get a better visual, right? But we have now, what are our dimensions for our volume? Well, your height is still x, right? It's going up x units. Then I have this little green section here, which was 10 minus 2x. And then I have this purple section here, which is just 10 minus x. So my dimensions here, this is the height. And then whatever you want to call your length and width, one is the length, one is the width. Doesn't matter really what you say, it's up to you. But we have our height, our length, and our width. So I would pause, I would do the rest on your calculator. But really the hard part is going to be setting these up. But pause, do the rest on your calculator, and see how you do. Okay, so when you graph, you should have a function that looks kind of like this here, my purple graph. So remember, the x-axis is representing your height. The volume is your y-axis. We had zeros of 0, 5, and 10, so I put my 0, my 5, and my 10 on there. Of course, it's a positive x times negative 2x times negative x has a negative 2x cubed, or sorry, a positive 2x cubed, because negative times negative is positive. So I have a leading coefficient of 2. Again, you're going to have your calculator though, so you can graph it, but you should know that your answers are going to be in between here, 0 and 5, so it just helps you to decide on your window. So part C says if the height of the box must be at least 2 inches, so 2 or more inches is what at least means, and the volume must be 75 inches cubed, determine the dimensions of the box. Well, I'm going to put in, for my y sub 2, 75, and it's going to intersect at 2 locations. But this first location is not at least 2 inches, so this one isn't going to count as part of my solutions. So I'm only going to use my second answer, which was 3.305. So that is my height. I subtract it from 10 to get my length, and I subtract it 10 minus 2 times that value to get my width. So my dimensions are 3.305 inches by 6.695 inches by 3.390 inches. Number 3, you should try this on your own, see if you can do it, otherwise we can do it together. So it says Simon wants to send a package by mail. The base of the package is rectangular with a length equal to 2 times its width. So clearly this is a shorter one. We can call this x is the width, so the length is 2x. The Postal Service imposes a restriction that the perimeter of the base plus the height of the box cannot be any more than 72 inches. So the perimeter of the base plus the height has to be less than or equal to 72 inches. So let's just say we're going to make it equal to 72 because that's the max it could be. All right, well, the perimeter of the base, so that's 2x times 2x times x, so it's 2, 4, 5, 6x, plus the height has to equal 72. So in other words, the height, in terms of x, is 72 minus 6x. So here is the height right here. I guess I can use a different color, right? So we're saying that height is 72 minus 6x. Okay. Part B, it says if the width of the base of the box is given by x, write an equation for the volume of this package. So, okay, so we already did that, the width. So the volume of the package is length times width, 2x times x times height, and we just said the height was 72 minus 6x. So this is the equation that we're going to use. Then you go ahead and you graph it. So when we graph it, we have a 0 at 0. Actually, we have 2 zeros at 0, so it's a double root, so it's going to bounce away. And then we have a 0 at 12. So 72 divided by 6 is 12, so we have a zeros there. Now if I were to multiply this out, 2x times negative 6x squared equals negative 12x cubed, so it's going down this time, right? It's a negative leading coefficient. And so I have to start by going down and end by going down, so I know my answers are somewhere between 0 and 12. It says, find the dimensions of the largest possible package that George can send, or sorry, was that his name? Or Simon can send. So we're trying to find, so what does my x-axis represent, right? What does my x-axis represent? That represents the width this time. And my y-axis always represents the volume. So I want to know what this value is right here. So this value is 3072. So find the dimensions for the largest possible package. So that would be 8 inches by 16 inches by 24 inches. So 8 by 16, plug it in here to get 24. And there we have it. This last example, you can go ahead and log on to YouTube. You can try it on your own. but log on to YouTube or just look at the answer key. If you get all the answers from the answer key, then you don't need to bother to watch the video. Or if you don't get the answers, then go ahead and type this into your URL so you can watch the video if you need it. Okay, see ya.